Hello everyone. So today I want to talk about logarithmic derivatives and implicit functions. How to get derivatives of implicit functions. So let's look at what we want to talk about. I want to talk about a function of the form f of x, which is equal to ln of x. How do we get the derivative? In other words, what is f prime of x in this case? So this is the first function I want to look at. And another type that I want to look at what is called an implicit functions. So that means the functions of the form x squared plus y squared, which could be even more complicated to have 16y. So a function which is a bit complicated like this. So now the question is, what is y prime? How do you get the derivative here? How do you get the derivative here? So this is what we want to look at. But first, what do I need you to know by now? So by now we need to know that you need to know that the limit as x goes to 0 of 1 plus x to the power 1 over x is nothing but e, which you remember last time we said is some very close to 2.1, 2.7, 1, 2.7, and with other numbers there, roughly 2.7. So let's leave it there. So it's roughly 2.7, but remember it's an irrational number. It doesn't terminate. It's so long. So this is just a rough estimate. So now, if you don't know these results, don't worry. Take your time, go back to the table, use the table and try to come up with this result to convince yourself that if you approach 0 from both sides, left and right, you are getting as close as possible to 2.71, which is the value of e. That's why we are saying as you approach that part, you get the value that is very close to e. What I want to talk about now, I want to start first with logarithmic. So I want to start with logarithmic derivatives. This is what I want to look at. And in fact, I want to start like, suppose we are given. So suppose we are given f of x. For simplicity, let's start with just a simple example. F of x equals to ln of x. And we want to find the derivative of this function. So this is what we want. So we know by definition f prime of x will be given by nothing but the limit as h goes to 0 of ln. Now you know how to substitute, you know the first principle definition, so I'm just going straight into the substitution. Ln of x plus h minus ln of x, which is f of x, and then divide by h. This is what you know, and I think now you are very good at this. And you can see that we can put together this numerator term using the rules of logarithmic from algebra last year to have the limit as h goes to 0 of ln of x plus h over h over not over h over what? Over x, because it's minus ln of x, so over x, the whole thing still needs to be divided by h, because we still have h here in the denominator. So which implies our f prime of x is nothing. I can start by within the limit as h goes to 0 and then put 1 over h this side, and then have ln of x plus h over x, which is sometime like this. And I can even make it look much better to write it in the form of the limit as h goes to 0, you still have 1 over h, then you have ln of 1 plus x over not x, 1 over, yes, 1 over h over x by separating the two fractions right here. Once you split the two fractions, the x will cancel, then you have 1 plus x over h over x. This is what we have for now. So now to proceed from here, I would like to do the substitution. So let's let u to be equals to h over x, and then which implies that wherever we have h, we can put u times x. And one thing which we note here is that as h goes to 0, looking at this expression or this expression, you will find that u will also go to 0. So these are our new limits. Our new limits for u is this one. So let's get our derivative right now. So now what we get from our derivative, it means f prime of x is nothing with the new limits, so we have the limit as now u instead of h. Remember, now we are plugging in u, so we are taking our limit with respect to u now. Wherever we have h, we substitute, so we have 1 over h, so 1 over h will be 1 over u times x, and then we have ln, inside ln we have 1 plus u, so we have this kind of expression. We can move a little bit further because you can see we can split this into two fractions here. So in fact we can take out 1 over x completely because it's just a constant. So you can have 1 over x completely outside because you're taking your limit with respect to u. So you have u, the limit as u goes to 0 of nothing but 1 over u times ln of 1 plus u. This is what we have. And you can go a little bit further to say the derivative now becomes 1 over x, the limit as u goes to 0 of what? Remember, with the rules of exponents, we can take this part and then put it here as a power. Even if it's a power here, we can take it back. So the movement is free there. Remember the rules of exponents from our algebra. So we have ln of 1 plus u raised to the power 1 over u. I think now you see where we are going. And you also see now why we had that results which we said you should know. And remember you can pass the limit into the function. You know the rules of limit now. So you have 1 over x. Then we have ln of the limit as u goes to 0 of 1 plus u raised to 1 over u. So you have passed the limit now into the ln. Now when you are here, this is the results which we said you should know that this is nothing but e. So we can plug in that value of e here, which implies f prime of x is equal to 1 over x ln of e. And you should know by now from last semester that actually ln and e, or ln is nothing but, let's write this part so that we have ln as log base e. So you know that this term is nothing but 1. So you are left with nothing but 1 over x. Therefore, we can conclude that the derivative of this logarithmic function is nothing but 1 over x. Good news for this portion. But there's still a long way to go because we need to extend this. So now let's do some extension, a little bit of extension before we go to implicit differentiation. Extension to more complicated functions. So we can extend this idea to more complicated functions. What are we talking about here? Which functions are we referring to? E.g., you may be given, let's say a f of x being equals to ln of x cubed plus 1, and then also let's say number b, you are given, to make it more interesting, g of x to be equals to log with base a, and then let's have x squared minus 1. So you may have some function of the sort. In fact, let's write it right here. So number b, you have g of x being equals to log base a of x squared minus 1. So you can see it looks a little bit more complicated, but we want to get an idea now to demonstrate how you can extend that definition that we have just done before, how to find the derivative of ln of x, now getting a more complicated function. So now you want to find f prime and g prime. So that's what you want to find. So let's see how we will get this one. Let's start with number a. Number a, you have f of x being equals to ln of x cubed plus 1. So the best way to go about this one is to let again. Let u be equals to x cubed. Always try to make your life simple. Wherever you find a complicated problem, try to let and then make it more simpler. Once you do this, it implies that if we were to take the derivative of u respect to x, you would get nothing but 3x squared by power rule. And then now let's go back to f. It means now we can write f as a function of u. That means now f can be equal to ln of u. So which implies that now the derivative of f will be nothing but by chain rule. Remember, you know chain rule now. It means now that f depends on u, we cannot start directly to find derivative of f respect to x. So we can say du first of what? Of the function that is given, which is ln of u, and then remember to multiply it by du dx. That's the chain rule. And then if you do that, the first portion is what we got from our first principle in our previous example, except that now instead of x we have u, but the same principle works. So you get 1 over u as a derivative, but multiplied by du dx. And always, if we're given function in terms of x and we made a substitution, leave your function the way it was given. Leave it in terms of x. That means we need to substitute back what is u and then substitute du dx. If we substitute back what is u, we have 1 over x cubed plus 1 times du dx, which is 3x squared, which implies that the derivative of f of x, which was given, is nothing but 3x squared over x cubed plus 1. Interesting. This is very, very important, because remember when we had ln of x, when we differentiated, we got 1 over x. So people are tempted to think that we'll always get 1 over x. No, that is not true. So you can see now with a substitution we are getting a more complicated. People will be tempted to just say the derivative of this is just 1 over x cubed plus 1, which is wrong. But you still have this term which came from our substitution using chain rule. So be careful about that before you do the conclusion. In fact, in a more general sense, if you are given f of x, let's say you are given f of x, which is let's say in the form of g of x to be in this form, then the derivative of f will be nothing but the derivative of g on the numerator divided by g of x. So you can see that for x we're lucky because the derivative of x is already 1, so it looks like we just had 1 over x. Actually we had the derivative of x over x. So this is in a more general sense what you should have. Let me make a note of b so that you'll complete number b before we go to the next part of this lesson. So for number b, you have f of x being given by log base a of x squared minus 1. So for this one you can write it, you can do the change of base like you know from the previous. So you can have log base e of x squared minus 1 and then divided by log base e of a, and then definitely you know that this is nothing but ln of x squared minus 1 and then divided by ln of a. You are back to where we were in number a. Then continue as we did in number a. This is where I stop. I give you a chance. As we did in number a above. So continue as we did in number a above. Let me go to the next part of the lesson today. Implicit derivatives. So implicit derivatives. So what are we used to? So far we have dealt with functions of the form. We have dealt with functions of the form. So what form are we talking about? Y is equal to f of x. But this is not always the case. E.g., some of the functions that we met y, which is equal to f of x, which is given by ln, just the one that we just met. We also met a function like y, which is equal to sine of x, so it's still a function of x. But how do we handle this function, which is x cubed plus y cubed, which is equal to 4xy. You see, here is very complicated. Even if you try to make y the subject rule formula, you're going to work very hard, and then you may not even get it. So to avoid, there is something that we're introducing today. The next one is something like x sine y plus cos 3y be equals to sine 2y. How do you deal with these functions in terms of finding the derivative? So in terms of finding y prime, how do we get y prime here? Let's see how do we get y prime. So we'll demonstrate using these two examples. So solution, let's look at number A. Suppose you are looking for dy dx of x cubed plus y cubed. So remember, you have to take derivative on both sides. So we'll take dy dx also this side, which is 4xy. So you are just applying dy dx. So the trick here is to treat y as a function of x. Treat y as a function of x. Every time you differentiate y, remember it depends on x. Okay. And then remember chain rule. That's another thing. So from this part, you can have dx of the first portion, which is x cubed, using your summation rule, and then dx of y cubed, and then you still have on the right, can take out 4, then you have d, because 4 is just a constant, of xy. Now the first part is easy. Straight away from here we get 3x squared. So you differentiate x with respect to x, you get 3x squared. Now the challenge comes when you get here. When you get here, you want to differentiate y with respect to x, but now we have y cubed here. So the best way is to apply chain rule. Start first by differentiating y with respect to y. That means you are differentiating y cubed with respect to y, and then remember you need to multiply by dy dx. That's chain rule. That's how we transform from this x to this portion, applying chain rule. And then on the right, you do the same, apply the product rule first. So it means you'll have dx of x, keeping y as a constant, plus when you keep x as a constant, now you get dx of y, which becomes nothing but dy dx. So that one is much better. So what we get here, the next step, what we get, which implies we still have 3x squared, but now we can differentiate this part because now I differentiate with respect to y. So we have 3y squared, but we still have dy dx, which is good because that's what we are looking for. We are looking for dy dx. So for the first part on the right, here dx is just 1, so you're left with just y. Then this part you will left with x times dy dx. You have just this part. We need to solve for dy dx, so we need to make it a subject here. I know you are good at that, so I'm going to skip those steps because now we are done with implicit differentiation just to make y the subject of dy dx with the subject of formula. So we have 3y squared. I hope I'm right. If I'm not right, you should be more right. Then you distribute the 4 inside there, 4x, and then this part, then outside we have dy dx. So this first portion comes from this, and then the last portion comes to the last term after distributing the 4 inside. So it means I've taken this part to the left, so I take everything to the right. Now you have 4y, and then you bring this term also to the right, then you have minus 3x squared. And then you can straight away get a derivative. That means dy dx is nothing but 4y minus 3x squared over 3y squared minus 4x, provided 3y squared, which we are dividing with, is different from 0. That's when we are safe, provided that is different from 0. So that's what we have. That's what we have. A similar procedure for number B. Let me look at number B briefly because now we are used to this part. So for number B, you want to get the derivative of x sine y plus cos 3y. You want to get the derivative of this, and then we also want to get the derivative on the right. So in this case, I'll be a little bit brief because we are used to this, which is 2y. So you want to get, so the prime here, you represent the derivative in this case. So if you do that, for the first part is a product rule again. So we differentiate, we keep sine y constant, we take the derivative of x, just 1, plus now we keep x constant, we take the derivative of y. Remember, if we take the derivative of that, so you're left with sine, you have sine y here, you want to take the derivative of this with respect to x. Let's keep it a little bit, we are coming to that. You come to cosine, you also want to take the derivative of cos 3y with respect to y, with respect to x, but we need to start with respect to y first. If we do on the right also, let's keep it like that, we'll come back to this one, sine 2y, then we want to take the derivative of this one. So remember, we still have here just sine y, and then we have x, but on this portion we need to be careful because now when we take the derivative here, we have to start first by taking derivative with respect to y, and then using chain rule, now we take again, we multiply by dy dx. So we'll have nothing but when we take derivative with respect to y, we have cosine y multiplied by dy dx, which is nothing but y prime, which is what we are looking for. And then this portion we do the same. We take derivative of cos 3y with respect to y first. Then we have 3 minus 3 sine 3y, and then remember you need to multiply by dy dx because we applied chain rule here again, which is nothing but y prime. So you go to the right hand side, you do the same. You have 2 cos 2y, then you multiply by y prime. Now we need to solve for y prime. We need to solve for y prime. Can bring the y primes together now. So we have x cos y, from this part. That's the first term. The next term is this one, which is minus 3 sine 3y, and then the last term is this one, which comes from the right, minus 2 cos 2y, and then you have y prime outside. What about on the right? You had nothing, so you just to take only this term to the right hand side here. If we take that, you have minus sine y. This is what you have. So, which implies our y prime is nothing but minus sine y minus sine y. Okay, let me write it properly, this one. Minus sine y being divided by x cos y minus 3 sine 3y minus 2 cos 2y. And this is our derivative finally. Using implicit differentiation, we managed to get our derivative. So, how do we conclude this lesson? We managed to be able to derive the logarithmic derivative, and then starting with a simple function of ln of x, and then after that we extended so that we can be able to handle complicated functions. By recalling that now we know how to use chain rule and other rules of derivatives, so we can manipulate a lot of functions using that. Next, we came to implicit differentiation, where your function is not explicitly defined, where we are used to y which is equal to f of x. Then we are able to find the derivative of that type of function. So this is what we have done for today, and we stop here, and good luck, and let's meet again next time to talk about L'Hospital.